The Standard Model of Particle Physics. The Standard Model of Particle Physics is a theory that explains the fundamental building blocks of the universe and the forces that govern their interactions. It is one of the most successful scientific models ever developed and has been confirmed through countless experiments. In simple terms, the Standard Model helps scientists understand what makes up everything around us, from stars to planets to the smallest atoms. At its core, the Standard Model describes two main types of particles, fermions and bosons. Fermions make up all matter, while bosons are the force carriers that allow fermions to interact with one another. Let us break these down into simple categories. Fermions are particles that make up matter, such as the atoms in your body or the materials in a chair. They are divided into two groups, quarks and leptons. Quarks, these are fundamental particles that come together to form protons and neutrons, which are the particles found inside an atom's nucleus. Quarks are never found alone, they always group together in combinations of 2 or 3. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. The up and down quarks are the most common because they make up protons and neutrons. Leptons, these are also fundamental particles, but unlike quarks, leptons can exist on their own. The most well-known lepton is the electron, which orbits the nucleus of an atom. There are 6 types of leptons: the electron, muon, tau, and their corresponding neutrinos, electron neutrino, muon neutrino, and tau neutrino. Neutrinos are very light and hard to detect because they hardly interact with anything. In the Standard Model, the forces that control how particles behave are transmitted by particles known as bosons. These bosons are responsible for the fundamental forces of nature. There are 4 fundamental forces, and each has its own boson. Electromagnetic force, this is the force responsible for electricity, magnetism, and the light we see. It acts between particles with an electric charge. The boson that carries this force is called the photon. Photons are the particles of light. Strong nuclear force, this force holds the nucleus of an atom together by keeping protons and neutrons bound to each other. The force carrier for the strong force is called the gluon. Weak nuclear force, this force is responsible for certain types of radioactive decay. It helps change one type of particle into another and plays a role in the fusion reactions that power the sun. The weak force is carried by 2 bosons known as the W and Z bosons. Gravitational force. Gravity is the force that pulls objects with mass toward each other, like the Earth pulling you down. Although gravity is not fully explained by the Standard Model, physicists suspect that if gravity fits into this model, its force would be carried by a hypothetical particle called the graviton. However, the graviton has not yet been observed. One of the most famous discoveries in recent years is the Higgs boson, often called the God particle. The Higgs boson is associated with the Higgs field, an invisible field that exists throughout the universe. The Higgs field is crucial because it gives mass to particles. Particles interact with the Higgs field as they move through space, and the more they interact, the heavier they become. The Higgs boson is the particle that confirms the existence of this field, and its discovery in 2012 was a huge milestone for physics. The Standard Model is successful because it explains a wide range of phenomena in the universe. It describes the interactions between particles in a way that matches experimental results. It accurately predicts how particles will behave in high-energy collisions, like those produced in particle accelerators such as the Large Hadron Collider (LHC) in Switzerland. Scientists use these accelerators to smash particles together at nearly the speed of light, breaking them apart and studying the fundamental pieces. The results have repeatedly confirmed the predictions made by the Standard Model, further solidifying its place as the most reliable framework for understanding particle physics. Although the Standard Model explains a lot about the universe, it is not a complete theory. For one thing, it does not account for gravity. Gravity is the weakest of the fundamental forces but is also one of the most important, because it governs the structure of the universe, including the formation of planets, stars, and galaxies. Additionally, the Standard Model does not explain dark matter and dark energy, which are believed to make up most of the universe. Dark matter is thought to be a type of matter that does not interact with light or normal matter, making it invisible, while dark energy is the force driving the expansion of the universe. Another limitation is that the Standard Model does not explain why there is more matter than antimatter in the universe. Antimatter is a mirror image of regular matter, with opposite charges. When matter and antimatter meet, they annihilate each other, leaving behind only energy. Yet, for some reason, there is far more matter in the universe than antimatter, and the Standard Model cannot explain why this imbalance exists. Physicists are searching for a more complete theory that can unify all the forces of nature, including gravity. One possible candidate is string theory, which suggests that all particles are not tiny points but rather tiny vibrating strings of energy. String theory also proposes that there are additional dimensions beyond the three spatial dimensions we experience. Another approach is called quantum gravity, which attempts to explain how gravity works at the smallest scales. The ultimate goal is to find a theory of everything that can explain all the forces and particles in the universe. The Standard Model of particle physics is a remarkable scientific achievement. It explains the fundamental particles that make up the universe and the forces that govern their interactions. While it is not a perfect theory, and there are still many mysteries left to solve, it has been extremely successful in predicting and explaining a wide range of phenomena. The discovery of the Higgs boson confirmed one of the last missing pieces of the Standard Model, but scientists continue to push the boundaries of what we know. The future of particle physics may bring new discoveries that extend or even replace the Standard Model, as we strive to understand the deepest questions about the nature of reality.